A new megaport on Peru's coastline, built as part of China's Belt and Road Initiative, is set to increase shipping traffic to Asia this month, introducing a direct route to China that cuts sailing time by nearly 10 days. A once quiet stretch of Peru's Pacific shoreline has just experienced an earthquake. Not a natural one, but a human-made shock. For years, engineers triggered controlled blasts and dropped multi-ton stone blocks to compress the soil, sending vibrations through the ground for kilometers. They relocated millions of cubic meters of sand and rock, enough material to fill the Great Pyramid of Giza several times over. All of this was done to construct a port so deep it can fully accommodate the world's largest cargo ships, and so resilient it's engineered to survive an 8.5 magnitude earthquake. But connecting this port to global trade required solving an even greater challenge. How do you transport millions of tons of cargo without destroying the small town and its path? How do you build a port on unstable soil in one of the most seismically active regions on Earth, and carve a hidden highway beneath a living city? Just a few years ago, Chancay was a sleepy district located 80 kilometers north of Lima, Peru's capital. Its economy was modest, centered on fishing, farming, and tourism. But beneath its calm exterior was a rare natural advantage: exceptionally deep water, an uncommon feature along South America's shallow Pacific coast. A former Peruvian naval officer recognized this potential in 2008, beginning a long and difficult land acquisition process. By 2019, the project transformed from a local vision into a global one. China's state-owned shipping giant COSCO acquired a 60% stake, partnering with local mining firm Vulcan. This was no longer just a port expansion. It became a $3.5 billion megaport, a vital node in China's globe-spanning Belt and Road Initiative. The goal was clear: build a direct maritime bridge between Asia and South America, a true continental gateway. But first, engineers had to conquer the land, the sea, and the violent forces beneath them. The first enemy was the ocean. To create calm waters along one of the world's most powerful coastlines, engineers needed a barrier, not an ordinary one. At Chancay, they constructed a massive breakwater stretching nearly 2.7 kilometers into the Pacific, longer than 25 football fields laid end to end. Its sole purpose is to absorb the brutal energy of Pacific swells, waves that travel thousands of kilometers before crashing into shore. To accomplish this, engineers deployed over 25,700 enormous concrete blocks known as acropodes. These interlocking structures weigh about 10.5 metric tons each, heavier than 2 adult elephants. Their multi-legged design disrupts wave energy, breaking it apart before it can reach the harbor. In total, more than 113,000 cubic meters of concrete were used, each block precisely placed with cranes guided by real-time 3D positioning systems. With the waves controlled, depth became the next obstacle. Modern megaships are colossal, some over 400 meters long and capable of carrying more than 18,000 containers. To handle them, the port required serious depth. Dredging crews worked non-stop, excavating the seabed to achieve a minimum depth of 17.8 meters, roughly the height of a 6-story building. This allows fully loaded 24,000 TEU container ships to dock without touching bottom. But these solutions created another problem. How do you connect such a massive port to the Pan-American Highway without flooding Chancay with endless truck traffic? The solution was underground. Engineers undertook one of the project's most ambitious feats: excavating a 1.8-kilometer tunnel directly beneath the town. This underground corridor would become the port's invisible lifeline. The challenge was extreme. The soil was not solid rock but loose sand and gravel, notoriously dangerous for tunneling. One miscalculation could cause surface collapse, endangering homes and streets above. To succeed, engineers relied on the new Austrian tunneling method, or NAT. This approach involves excavating small sections and immediately reinforcing them with sprayed concrete and steel arches, allowing the surrounding earth to become part of the structure. In some sections, the tunnel ran just 6 to 9 meters below the surface. Precision was critical, with allowable surface movement limited to less than 1 centimeter. Inside, the tunnel is a technical masterpiece. It spans 14 meters wide with 3 dedicated truck lanes, allowing cargo to bypass the city entirely. It also contains 2 massive conveyor belts for grain and bulk materials, along with pipelines for liquid cargo. This underground system allows the port to operate at full capacity without adding a single traffic jam to Chancay's streets. Once containers exit the tunnel, automation takes over. The port operates with colossal machinery. The ship-to-shore cranes lining the docks were built by ZPMC, a global leader in port equipment. These cranes rise over 90 meters tall, taller than a 25-story building, with a reach of 72 meters capable of spanning the widest ships afloat. Most impressively, they are remotely operated. From a control room, a single operator can manage multiple cranes with joystick precision, loading and unloading containers at remarkable speed. Containers are then transferred to autonomous electric trucks that navigate the yard using advanced sensors and AI algorithms. These vehicles deliver cargo to automated stacking cranes that organize containers with flawless efficiency. This integrated system is designed to achieve a staggering goal: 50 container moves per crane per hour. Most of the world's top ports average around 30. This efficiency is what allows Chancay to dramatically reduce shipping times to Asia. Yet all this technology would mean nothing if it couldn't survive nature's greatest threat. Peru lies on the Pacific Ring of Fire, responsible for nearly 90% of the world's earthquakes. From the ground up, Chancay was engineered to withstand an 8.5 magnitude quake and the tsunami that could follow. The biggest danger isn't just shaking, but liquefaction, where saturated soil behaves like liquid, causing structures to sink or collapse. To prevent this, engineers strengthened the soil itself using deep soil mixing and vibrocompaction, installing reinforced aggregate columns deep underground to create a stable foundation capable of surviving extreme seismic forces. The massive breakwater also serves as a first line of tsunami defense, designed to absorb and deflect the energy of seismic waves. Construction of Chancay has been a race against time. Its first phase, a $1.3 billion investment, officially reached trial operations in November 2024. But the project has not been without controversy. Local fishermen argue the breakwater has disrupted marine currents and damaged fishing grounds. Residents report structural damage from constant construction vibrations, while environmental groups warn of harm to the nearby Santa Rosa wetlands, a critical habitat for migratory birds. While the port is expected to add $4.5 billion annually to Peru's economy and generate over 8,000 jobs, it has also raised geopolitical concerns, with the United States wary of China controlling such a strategic asset in the Americas. As Chancay ramps up operations, it stands as a symbol of extraordinary engineering ambition, a massive structure of concrete and steel that has reshaped an entire coastline and is poised to redefine global trade routes. The Port of Chancay is more than just a harbor. It is a powerful statement about the future of global logistics, built with precision, scale, and force. If this impossible build amazed you, hit the like button, subscribe for more deep dives into the world's most incredible engineering projects,